I believe we left off ready for number 4, yes? And number 4, we're being asked to find inflection points and the open intervals of concavity. What do we need here? Excuse me.
Derivative.
Connor's like, I don't know. What derivative?
Second derivative.
Second derivative, right? Second derivative tells us all about concavity and inflection points. So, first derivative is 1/2 plus cosine x. Second derivative is negative sine x. Okay. Now, in order to find our critical values of the second derivative, we're going to set this equal to 0. Okay, so we want to know, when does negative sine x equal 0?
I have no idea what.
It just so happened in the previous lesson we didn't do the bottom of the right page.
Oh,
So I
okay.
opened that thinking that's where we're at.
Okay, you're in the total wrong
You're
lesson.
distracted.
At 0.
Okay, so whatever your method is, I know I don't think you guys go for my method. I think about my graph, and I know my zeros are at 0, pi, and 2 pi. Now, why did Miles add 2 pi? Because this interval says 0 to 2 pi, yes? Now, here's the idea though. I mean, those are going to be our endpoints is what's happening. And when we talk about this, we're going to be talking about on the open interval when we give our answer. So those are the endpoints that we have to worry about. So we're not really, I guess what I want to say here is our focus is going to be pi, because 0 and 2 pi are going to be my endpoints. So set up your number line to test. The endpoints, because we're on the interval 0 to 2 pi, are 0 and 2 pi. And we have a pi in here. This is our second derivative. We're trying to test for inflection points, concavity. So when we plug these values back in, we're plugging them into the second derivative. Oh, you know what? I guess it's supposed to be g, isn't it? If I want to get specific. This problem is not f, it is g. So this is going to be g double prime. So if I pick a value here and plug into from 0 to pi, my brain, I'll tell you, and not that you have to write it down, my brain's picking pi over 2, because that's an easier thing to work with. Okay. Sine of pi, so it's negative sine of pi over 2. Sine of pi over 2 is going to be up here at positive 1, but the negative of that is going to make it negative. Okay. And what does a negative second derivative mean? Concave down. In between pi and 2 pi, my brain's picking 3 pi over 2. Sine of 3 pi over 2 is down here at negative 1, but the negative 1 is going to make it positive. Positive second derivative indicates concave up. Did you say smiley face? Smiley face or frowny face? Got it. Okay, now what do we need? Find the inflection points. Do we have an inflection point? Yes, because concavity changes at pi, right? So if it wants us to know the point, we do need to find what is g of pi. We need to find that information. When you're trying to find the actual point, you're plugging back into the original problem. So 1/2 times pi plus sine of pi. So g of pi is going to be, I would write that as pi over 2. No, plus 0. Sine of pi is just 0, right? So, excuse me. I would just write that as pi over 2. So, information to state. We have an inflection point at g of pi equals pi over 2, however you want to say it. You could also say, write it as an ordered pair. That would be okay as well. Why is that an inflection point? Since the second derivative changes from negative to positive. I did say justify, which is why I'm writing that out. It also asked us about open intervals of concavity. And so we know that this is what? Concave down on the interval 0 to pi. And why is it concave down? Since the second derivative is negative, or less than 0 is what I'm going to write. I guess I should have probably said is, oh well. G of x is concave up on the interval pi to 2 pi. And that is because the second derivative of x is greater than 0. Okay. Gets us back in the groove, right? Let's go look at 5 and 6. In an effort to try and make sure we get through a little bit of everything, I'm probably going to maybe do 5 but skip 6 because they ask a very similar question. They both say use a calculator. And the idea is to find how many times this graph changes concavity on the interval 0 to 2 pi. Thoughts? When we're talking about concavity, we're going to need to know the second derivative. She had a way to find the derivative on her calculator, but her calculator wasn't Inspire. So this calculator, this is not bad. I mean, it's not perfect, but we can do this by hand. So first derivative is 2x minus nothing plus the derivative of sine of something is cosine of something times the derivative of something. So I'm going to write this as 2 cosine 2x minus 1, if you will. In other words, I went ahead and put my 2 out front. That 2 out front is the chain rule 2. Second derivative. Derivative of 2x is 2. Okay. There's already a 2 out front, yes. Derivative of cosine of something. Okay, so it's going to be minus, there's already a 2 out there, sine of something times the derivative of something. So times another 2 in there. So my second derivative is really going to clean up to be 2 minus 4 sine of 2x minus 1. If I did that right?
Wait, so how did we get the second 2?
The chain rule again. So this 2 carried down.
Right.
And then this 2 would be when you did the derivative of cosine of something being negative sine of something times the derivative of something. So the derivative,
So instead of being
I went ahead and put it at the beginning. Okay. And it's one of those things. You can put it at the end. But then eventually with cleanup, we usually put those types of things in the beginning. Especially with a trig function, we usually put that in the beginning. Okay, so how do we figure out where this changes concavity? Okay. How do we find those points? Okay, we usually talk about setting this equal to 0, yes? So the idea is we want to know, when does my second derivative equal 0? Now, it said use a calculator, right? How can my calculator make life really easy right now?
Grapher.
Grapher. And what are we going to look for in that graph? Zeros, because we want to know when does our second derivative equal 0. So we're going to graph the second derivative, and we're going to look for our zeros. So we're going to graph the second derivative, and then we want to know when it says when does the second derivative equal 0. Actually, oh my gosh, didn't erase. So then the question is going to be zeros. Now, there's an interval on this one, isn't there? Make sure you're looking at the right interval. I know I had this graph saved in my calculator, but then I cleared it out because I've loaded this calculator out a couple of times lately. So 2 minus 4 sine of 2x minus 1, right? For trig functions, I like to use z7 instead of z6, which is just a trig. Instead of counting 1 through 10, it counts by pi over 2s. Oof. Now, where do I need to look? 0 and 2 pi. Can you change that on your window so you know where we're looking? Yeah. I'm going to go, I already hit Z7, which was the Z trig. And then if I go into my window, I can change my, why does that not look right?
That is not what mine said.
Yeah.
No, it's not.
Okay, whoa. I loaned this calculator out
Degrees.
for a physics test.
Degrees.
Did you give it
That's a
to?
good one.
Hannah, because I screwed up, I was supposed to be charging your calculator, and I was charging Peyton's first, thinking I'll get Hannah's later. Forgot, oh, Hannah and Peyton both have physics in their calculator, and, okay, hold on.
This is her. So, basically what you do is you X out and then X that and then X out of
2
graph.
minus 4 sine 2x minus 1. I'm in radians now. Trying to think what else is, okay, let's do zoom 7. There we go.
Much better.
Sorry, guys. I made sure to change my calculator to degrees for Hannah just in case, like, you know. Okay. Now, my window settings. There we go. For -8 something to 8 something. I want to change my x-min and x-max to be 0 and 2 pi. And then regraph it. And now the nice part about this is I'm looking specifically at the interval in question. So, what do you know? There are 4 zeros. And what was my question? How many times does the graph change concavity? What are we able to hopefully assume here? That there are 4 places. And if you look, each time, each of those zeros, my graph is changing from negative to positive or positive to negative, isn't it? Okay, because the original graph is what we're talking about. How many times does it change concavity? The zeros of the second derivative are telling me that. So 4 zeros, which means 4 times since second derivative has 4 zeros. I have them written. As a side note, I went through and found the zeros and wrote them in my notes, but what did the question really ask? How many times? Could you find the places it changes concavity if you needed to? Why, certainly. Sounds like a waste of time for me right now, though. Okay? Now, I think with that in mind, we'll see how time goes. 6 asks us to find the values at which the graph changes concavity. Would it be a similar setup? Find the second derivative, and then you could graph it, right? And you can find, it'd be basically doing this, but finding the actual zeros. So I'm going to skip 6 because I feel like it's very similar in terms of what you would do. And I'm going to keep moving. Again, if we have time, we'll be back. We have a lot to do today, though. So this is a chart that's just at the bottom of the paper. And so there's a lot of connection between your function, your second derivative, your first derivative. So the second derivative is the first derivative of f prime of x. So the same relationships that exist between f and f prime also exist between f prime and f double prime. We can use the second derivative test as an alternate method for locating relative extrema. So we talked about using first derivative test, right? Finding those zeros, and then where is it increasing or decreasing, and whether does that make a min or a max, okay? We can also do this with something called the second derivative test, and that's what I'm going to demonstrate on the next page. So to fill in the chart real quick, if c is a critical number, then the derivative either equals 0 or does not exist. This makes x equals c a possible maximum or minimum value of the function. So what do we know here? If my second derivative is positive, we know our original function is what? Concave up. Now, with that in mind, if the original function is concave up, then that means the first derivative is increasing. Ugh. If the second derivative is negative, that means my original function is concave down. My first derivative then would have been decreasing. If my second derivative is neither positive nor negative, that means it is, what are my options? It's either, 0 or undefined, does not exist. So what's that mean about the original, or my second derivative is either 0 or does not exist, then this is on the original function, it's possibly, I'm going to say possible point of inflection. And that means on the first derivative, it could be a possible extrema. So a possible min or max. Okay. Okay. 7. Let's demonstrate second derivative test here. Actually, okay, we can do debate. I think I might just do 7a or 7b. How do you feel about, should we do the trig one or the non-trig one? Well, the basic one, okay? Let's do the basic one. And there's one trig one in homework that I see. Okay. So, second derivative test to find what? Extrema. It's not second derivative test to find concavity and inflection points. It's to find extrema. So we handle it a little bit different. We're still going to have to find the second derivative, but first, we need to find the first derivative and its critical values. Okay? So, first derivative is 4x cubed minus 24x squared. We want to go ahead and find our critical values, critical points. So we're going to set equal to 0. There's a GCF of 4x squared. Factor out of 4x squared. We're left with x minus 6. Set each part equal to 0. And we get critical numbers at 0 and 6. Those are your critical values, critical numbers, critical points, whatever you want to call them. Those are the points that could possibly be mins or maxes, right? Okay. So, second derivative test. If we were doing first derivative test, we put these on a line and we test the first derivative in between them, right? Figure out where they're increasing or decreasing and go from there. The idea with second derivative is we want to look at what's happening at their second derivative. So, what is my second derivative? (12x squared minus 48x). Now, I don't need to know critical values for it. This is going to be where we're going to test, okay? We want to factor. We don't have to factor. Because we want to test these values. I want to know what is happening with the second derivative at 0 and what is happening with the second derivative at 6. Maybe you factored this to make life easier, maybe you didn't. When I plug in 0, what do I get? 0. When I plug in 6, what do we get? Should I tell you, or do we? Let's see a couple people. Yes? 144? So hopefully what the calculator says?
Mine's dead.
Did you say yours is dead?
Yeah. Wait, you didn't charge it? Oh.
Mine's getting
Yes.
close.
Wait,
Sophie's died during her test today, so.
mine died during my test yesterday.
How'd Mr. Kevin handle that?
He gave me his.
His little,
Jake,
like, 4 function calculator.
The importance of wanting to charge your calculator ahead of time, then.
Yeah.
Okay, now, what we have found here. Okay, so, let me fill in the chart and then we'll talk about this. I don't know why this chart's set up. Our x equals c values. Our c values are our critical numbers, which were 0 and 6, yes? I forgot. I didn't have us find f of c yet. These are just what the actual ordered pairs are going to be. So f of c would be okay. I didn't have us find f of 0 and f of 6. I forgot. What is f of 0 when we plug it into the original function? -5. And f of 6 when we plug it into the original function.
Why does it say F when we're on the sheet?
Because obviously she is as bad as I am. Yeah. I'm horrible about that. Everything is F in my brain and
well, like AP, like not wants to do that.
I don't know. I don't think so. But I don't know.
Like, I mean, if you're
Yeah.
discussing with like F and G, like
Yeah.
it was in the same question, I can see it. But like something like this.
When it started with G and we accidentally switched to F's, exactly. Obviously, it matters if they're both in the same problem, but if there's only one in the problem, what else could you be referring to? Unless you define a new function or a new equation or something. But okay, f of 6 was negative 437. Okay, second derivative. The second derivative, which was 0, which I'm concerned about positive or negative, and that is just 0. My second derivative at 6 was 144. What do we know about 144? It is a positive value. Okay, guys. The 0 is inconclusive. That doesn't tell me if it's a min or a max. Now, what does a second derivative tell you? Don't answer min or max here, but what does second derivative tell us? If it's positive. It says what? Concave up. Is concave up going to result in a min or a max? Does that make sense, sir? That's how the second derivative test works. Is that because there is a second derivative that is positive, that means concave up, and a concave up section of a graph is going to result in a minimum. Okay? This one, because it's 0, it's not going to be a min, it's not going to be max, it's probably going to be an inflection point. Okay? I can't say that definitely, but that's probably what's going to happen. Okay, so, fun word here. Justify. So, I will start with, there's a local min at, let's see, x equals 6 of negative 437. That is very minimum. It's a very low number. And why is this? This is because or since the second derivative is greater than 0. I always have to stop and think about this one. Second derivative is greater than 0, and thus G is concave up. Okay. And then we could also say no conclusion at x equals 0 since G prime of 0 or x is 0. Am I hearing things?
No, that's your first.
Oh. Oh, I bet Logan did too. Take an extra for him. Be a helpful sister.
Is that supposed to be G double prime?
Yep. Okay. Oh, okay. So now, for reference, what does this graph look like? It looks something like that. Does that make sense then with what we figured out? Because what is this? Here is your minimum, right? At x equals 6. And at 0, what are you seeing? Looks like it's going to be an inflection point. Okay, so that's likely a point of inflection, but that's not what they even asked us for, is it? They asked us for extrema. Okay. Does that give us an idea there? Okay. 7 would be similar. The trick on 7 is that it's trig, and so you have to think hard there. Okay. Let's look at 8 some. Okay. So 8. The graph of what? Always pay attention to this, guys. I cannot stress this enough. They're not always going to give you the function graph. It could be the derivative. It could be the second derivative. Okay? Hayden, only 2 more lessons to get through, right? Okay. So the first derivative is shown. So on what intervals is f increasing and justified? So when is f increasing? When the what is what? When the first derivative is greater than 0, aka positive, yes? This is what my brain has to go through, so I'm assuming your brains will need some of this too. So, where is that on this graph?
Negative infinity to A, then B to C.
Are you guys with us? This is the first derivative graph. The question is about f. So I'm not looking at, oh, my graph is increasing from -1 to 3. No, f prime is increasing from -1 to 3. This is the derivative. And so right here, this piece of the graph is positive, yes, and that piece of the graph is positive. Now, maybe I didn't want to write those positives and negatives in. Here, I'm gonna change my mind. I did. So right here, derivative greater than 0, derivative greater than 0. So we can say f is increasing on -infinity to a and b to c. And why is that? Because the first derivative is greater than 0, aka positive. Okay. At what values of x does f have a local max or a local min? Justify. When do maxes and mins occur?
Zeros.
The zeros of the first derivative, right? So these happen, when the derivative equals 0. That's what my brain is processing. Normally to find my mins and maxes, I take the derivative, set it equal to 0. So those happen when my derivative is equal to 0. Now, so what do we need to look at here? ABC, right? And I'm actually, maybe you guys don't need this, but I'm going to set this up just to maybe be helpful. If you think about a number line for f prime with a, b, and c. Okay. What do you know about the derivative to the left of a? It is what? It is what? Yes. Sorry. I'm thinking ahead to another part. What about between a and b? My derivative is negative. Between b and c? Positive. C to the end? Negative. So, with that in mind, increasing, decreasing, increasing, decreasing. Where are mins? Where are maxes? What's A? A is a max. What's B? A min. And C is a max. Okay? You work it out however you want to. You think it through, but those are my thoughts. So I'm going to, let's see, it does say justify. So f has a local max at x equals a and x equals c because the derivative changes from positive to negative. And there's a local min at x equals b because the derivative changes from negative to positive. That is my information to write down. F has local, or you can say relative maxes at x equals a and x equals c, since f prime changes from positive to negative. F has a local min at x equals b, since f prime changes from negative to positive. Okay. Should have set this page up differently. Okay. C asks us to state the inflection points, right? Okay. When do inflection points happen? Inflection points are when the concavity changes, or so when the second derivative equals 0. So inflection points, we're looking for second derivative equals 0. Well, okay, think second derivative with me here. And I'm just trying to set up like another number line to help us think it through. As we think about second derivative, we don't have a graph for second derivative, do we? But second derivative is the derivative of first derivative, yes? So it's going to have to do with where this graph is changing from increasing to decreasing, right? It's kind of like looking at a function graph and the derivative is your slope, yes? The second derivative is the slope of the first derivative. Does that make sense? So what do we know? My slope starts off as negative. Where does my slope change? It's negative all the way through A. It's negative up until negative 1. Then what happens? At negative 1 to 3, my slope is positive. And then from 3 to infinity, my slope is negative. Now, this is a second derivative graph, right? So second derivative, the negative indicates that this graph is concave down. From negative 1 to 3, my graph is concave up. And from 3 onwards, my graph is concave down. So where are my inflection points? Negative 1 and 3. And why are those inflection points? Because,
slope is 0.
Okay, because the second derivative is 0 there, right? In other words, we've got right there, those pieces there. And I guess I don't have it, but it would also be because the concavity changes from negative to positive or positive to negative, right? So I have it set up here on the next page. Probably not my best idea, but F has inflection points at x equals, what was it, negative 1 and 3. Since second derivative is equal to 0. And changes from positive to negative, or vice versa. Okay. You know how to answer the next question now? I feel like we should. What intervals is the function concave up and concave down? Can you look at that number line you have? Flip back for a moment. We already said it basically, didn't we? When checking for our inflection points. So use that information on the fact that it's concave up from -1 to 3. So f of x is concave up on -1 to 3, and that is because the second derivative is greater than 0. So that means f of x is concave down on, what would it be? -infinity to -1 and 3 to infinity, and that is because the second derivative is less than 0. Okay, guys. Part E leads us into one of the next 2 lessons. I think our next lesson is curve sketching. And, okay, can you sketch the graph based on the information provided? And officially the answer is yes. You just have to put it all together. Okay, so now it does say assume that f of 0 is 0, so that's just saying there is an ordered pair at 0, 0, yes? What else did we talk about? Let's see. Part B said that there is a max at where? A and C, and a minimum at B. So I'm going to, I don't have it up here. Let's see. A was approximately over here. B and C are approximately over here. So what my brain's saying is, okay, I know somewhere above A, and we don't have a height, do we? But in my brain, I'm putting a point there, and I may change that point if I decide I need it higher or lower, because there's an A above max. Or, yeah, you know what I meant. There's a max above A. There's a, what else did we say? A max at C, and min at B. Well, that right there gives you a really good idea of what your graph's going to be doing, doesn't it? When you see those maxes and mins. Okay. We know it goes through 0, 0. This is the hard part to get it all in. There are inflection points at -1 and 3. Now, keep in mind, let's see, where was -1 was here, 3 was here. Inflection point is where my graph is going to change concavity. This is where I struggled to make it all come together. But you can see the shape, right? Just knowing the mins and maxes. We can see the shape that we're going to go up, come down through here, come down, come back up. Trying to get those inflection points to match up, well, I don't know. I'm trying to think, is there anything else that we really need to know? We also know it's going to be concave up from -1 to 3, right? Now, and I'm not saying that the inflection points are at that, it's just at those values. And it's concave down on those other pieces. So, okay, here we go. Okay, oh, man, I have to erase. I don't know. Okay. The thing I struggle with, I don't feel like my inflection points are right. That's my struggle. So, yeah, same thing happened when I was trying to sketch this out. I feel like my inflection point ended up more at 0 than it did at -1. Trying to make it happen. But the idea is there's supposed to be an inflection point at 3. I can see there being a point of inflection there. We've got our maxes. We've got our min. And then there's supposed to be an inflection point at -1. I guess you could call that an inflection point. That's the harder part to make happen, are the inflection points. But did we do it? Okay. Now, the key is when you're told to sketch a graph and they don't walk you through all those steps to begin with. It was easy at this point because we walked through all the steps we needed. Okay? Okay. 9 does a chart. Okay? And they give you some table information, of course. It tells us that the function is twice differentiable and continuous. Always helpful to know when they give you a chart, and they'll pretty much tell you that information. If they don't, so often our answers, we can't do it. We don't know if it's continuous. Okay, so A, explain why there must be a value of some number on the interval from -4 to 5 such that g of c equals 7. Okay, so when they say the interval -4 to 5, isn't that what we are given here? This is -4 to 5, right? So why must there be some point C where this function equals 7? You remember this? We've learned several theorems this year.
Is it something like this? IVT?
It is IVT. This is intermediate value theorem. And the idea is, now, what has to happen? Has to be continuous. I can't say IVT if it doesn't tell me it's continuous. So, because, and here's the deal. 7, so we know that g of -4 is 0, correct? G of 5 is 8. And we know this graph is continuous. If you connect the points -4 and 0 and 5, 8, your line has to go through the y value of 7, right? Whether you make it a line, a curve, whatever, it has to go through 7. So that's what intermediate value theorem states, that it must exist. And so mine says, since I put it as 0 less than 7 less than 8. So that's basically saying since 7 is between 0 and 8. And the other restriction, since f is continuous, you need to state that. And it's continuous on the interval -4 to 5. Then by IVT, there must be a value where this is true. Okay? By IVT, there must be some x equals c such that, I'm going to continue with my f, it's supposed to be g, isn't it? F of c, g of c equals 7. Dang it, all of those should be g's.
I do sometimes the brackets on the table and sometimes
Well, on this one, I'm looking at what was defined, -4 to 5. When we talk about our mins and maxes and concavity, it's usually stated to be done on the open interval. Open interval meaning parentheses. Closed interval meaning brackets, if you look at that vocabulary. Okay. B. explain why there must be a value on negative 4, 5 such that g prime of d equals 8, 9. When you're given a chart, how do we find the derivative? We basically do slope, average rate of change. Well, if you set up average rate of change here and do g of 5 minus g of negative 4 over 5 minus negative 4, guess what it so happens to equal? It's going to be 8 minus 0 over 5 minus negative 4, and it just so happens to equal 8/9. And again, this works because f is continuous and differentiable on this interval. Okay, this is mean value theorem. Okay, so I can say, since f is continuous, we talk about continuous, to go back to Megan's question, we use the closed interval, negative 4 to 5, and it has to be differentiable. So differentiable on the open interval, negative 4 to 5. Then, by MVT, there is a value, or g prime of d equals 8/9. I'm just going to write it that way. Okay. C,
What is it? And diff.
differentiable. Me trying to be quick. And I really struggle to spell differentiable.
What's the
And then what?
DM?
It's on.
Oh.
This?
Yeah, that does look like an S.
Nope, you're fine. And being quick on the board it writes differently too. That is for sure. Okay, C, if we have a moment to start thinking about it at least. Does G have a max, min, or neither at x equals 3? Well, x equals 3, what do you notice? The first derivative is 0. If the first derivative is 0, then it's a critical value, right? It's a critical value, and then you can look at, what do you know about the second derivative? Second derivative is negative. A negative second derivative indicates concave down, which indicates a max. Okay? So, I'm going to say it's a critical value, and I'm trying to shorthand, since g prime of 3 equals 0. And then, okay, that was weird. Concave down, since g prime of 3 is negative, less than 0. And so, because of that, we can say local max.
Is that double prime?
Yes, thank you, double prime. So, that is local max, and that is by the second derivative test. Okay? So, and we can't determine concavity. We can't determine concavity because we only have 3 points. We need all the in-between information. Okay? So, okay guys, go do the homework. 4, 6, 10, those are the ones with the very fun first and second derivatives. You can decide how much effort you want to put into 4, 6, and 10. Does that make sense? Because she doesn't show you any work. Have a good day.